Boom, here we go. So, welcome to circuits. Circuits are, just to be clear, I totally disagree with the change in the curriculum that puts circuits in grade 11. Because there was a whole, half of the grade 12 curriculum dedicated to electricity and magnetism. So to shove circuits here is going to feel really out of place. I get that. I want you to know that I understand that. It's weird that they've put it here, but they have, so we're going to do it. Nothing that we're going to do here is even remotely connected to anything we've done up to this point. Everything else built. Kinematics built, or measurement built into kinematics, kinematics built into dynamics, dynamics built into energy. All connects. This, totally out of left field, radically different. That's okay, we're going to do it anyway. So, we've talked about that. Maybe it's not you guys have talked about this, but maybe it is. Imagine you walk across a fuzzy carpet, touch a doorknob. What happens? Or, like me, you drag your feet as a child in Costco and then grab mom's hand. What happens? You shocked her. Why? What is that shock? Static electricity. What is static electricity? When you say electricity, what does that mean to you? What understanding of electricity are you guys walking into my class with? But what is electricity? What makes it static? Why when you say static, what does that mean to you? When you say static electricity, what does that mean to you? It's related to, so you've got ideas where charges repel each other. Which charges repel each other?
About this shock stuff.
Yeah.
Every time that I go downstairs, there's the metal thing that you use to hold it, and I just.
Oh, the railing on the stairs.
Yeah. Every time, I don't know why.
Because you're probably dragging your feet when you walk.
No, I'm not.
No, I would walk more consciously and check, because that thing's not hooked up to anything that would shock you. So the only source of that is going to be you. Now, if you were to lean up against the wall and get repeatedly shocked, well, then we have an electrical problem in the building. We need to get that dealt with. But if you're touching a railing and getting a shock, you're doing that to yourself. And so why that is, there's a few reasons why that could be. And unfortunately, we're not going to do, this chapter is called circuits, not electrostatics. It would make sense to start with electrostatics, which is where physics 12 starts, is with electrostatics. But here we are in circuits. So what do things mean to be, when things are static, what does that mean? We talked about static in one other place. That word static showed up somewhere else. It's not moving. We talked about it when we were talking about coefficients of friction. So we had static coefficient of friction and kinetic friction. When the thing's not moving, it has a particular value from you. When it is moving, it has a different value from you. Static friction versus kinetic friction. So static is when things aren't moving. So this is where we talk about charges repelling each other. Like charges repel, opposite charges attract. So if I have two electrons, they're going to repel each other. If I have an electron and a proton, they're going to attract each other. This is the basis for basically all of chemistry. But this is circuits. How is circuits different than electrostatics? Circuits require what? Needs to circulate something. Yeah. So we've got moving charges now in this case. So circuits require charges to move. What charges? We'll figure that out. The whole getting a shock thing. To get a shock, a charge has to move either from another object to you or from you to another object. And interestingly enough, it doesn't matter which direction the charges are going. It feels exactly the same to the person experiencing it. So in electrostatics, we play with the Van de Graaff generator. How many of you have a chance to play with the Van de Graaff generator before? Easton's class definitely should have. This is the one where it's the ball, you put your hands on it, you crank the thing, your hair stands up. You grab the poor pathetic sap next to you, and now they get shocked because they're not grounded to the Van de Graaff generator. I'm really sorry you haven't had a chance to play with that. If you have me for Physics 12, we'll play with it. Sometimes Morrison. But a shock requires a moving charge, and so that is the fundamental basis for all of current electricity. Current electricity is all about moving charges. Specifically, which charges do you think are going to be the ones doing the moving? Or maybe I'll ask a different question. What are the two fundamental charges? If I asked you to think of like a positively charged object or positively charged thing, what is the smallest positive charge you can think of? Positive. James? A proton. Yes. Protons are located where? What's that center called? A nucleus. Cool. So the nucleus is where all of the mass of an atom is held. Nucleus has protons, has neutrons. Protons and neutrons are heavy, very heavy, relative to the fundamental negative charge, the electron. Electrons are very light. They're in orbit around the nucleus. If something was going to move, if one of those charges was going to move, and I asked you to put money on which one was going to move, you would hopefully say which one.
I would say the electron would move because it's less electromagnetic, I think. But between the protons and neutrons, I really don't know because they don't sense any senses.
Well, think about where they are. If the protons moved, that means the nucleus of the atom is moving. If you had an object where all the nuclei of the atom were moving, what would that object be doing? The entire object itself would be moving. It would be, you'd have a desk that was oozing across the classroom if all of the nuclei were moving. Would that make sense? No, that would mean every time you plug anything in, all of the wires are like molding in the building to give you power, and that doesn't happen. So the only thing that can actually move here when we talk about moving charges are those much, much lighter electrons that orbit these nuclei. Do you guys know the relative difference in mass between protons and neutrons? Sorry, protons and electrons? Okay, to give you some perspective, an electron, I'll give you the proton first. In atomic physics or in quantum chemistry, we call protons, we say protons have a mass of 1. This is something you should have definitely seen before, either in Science 9 or Science 10. We assume protons to have a mass of 1. This is where the atomic mass of these things come from. You sum up the protons, you sum up the neutrons. That's the atomic mass. Why can we ignore electrons? Well, we can ignore electrons because I don't remember the exact number, but if a proton weighs 1, and protons, remember, are very, very small already, electrons weigh 0.0005 of a proton. And protons are already incredibly small. So an electron is that much smaller relative to a proton. These are the things that are doing the moving. So when we talk about moving charges, what we ultimately are talking about here is a flow of electrons. Because the nuclei of these objects aren't going anywhere. In grade 9, if you talked about electricity at all, maybe I'll just give this to you out of electrostatics. In electrostatics, there is a concept here called Q. And believe it or not, Q in electricity is different than Q in energy. Q in energy was thermal energy. Q in electrostatics is total charge. And what we do is we give total charge as a multiple n. This is just the number of charges. I'll zoom in here so it's easier for you guys to see. Number of charges times the fundamental charge, or the elementary charge here, which is E. Which I'll give to you down here in this section. So the total charge Q is given to you by the number of charges N times the elementary charge E. This should make sense, I hope. This is, again, something that's going to show up in electrostatics, but we kind of need to at least address it before we can just jump into circuits. Circuits, we care about charges moving, though. So a moving charge we call a current, and it is related to this idea, the amount of charge flowing per second. So the current I is equal to the amount of charge Q flowing per second. So it's Q over T. And if I'm not mistaken, I definitely forgot to put this on your guys' formula sheet. So we're going to do some adding to the formula sheet here in a little bit. So have that thing handy. So you've got I equals Q over T. This is the amount of charge past a particular point in the circuit for this many seconds. We can do some substituting here. We can say that, well, Q is just the number of charges times the number of the charges times the elementary charge. So I could also write current as NE over T. Where I is, let's fill in some of these variables now. I is current. Does anyone know what current is measured in? What units? It's measured in amps. Sweet. And the letter we use for that unit, you would probably guess is? Capital A specifically, yep. T is time. Time is always measured in seconds. Q is charge. Does anyone know the unit of charge? Sorry? One more time? No. Voltage is a different beast entirely. We'll get to voltage. Charge is measured in something called coulombs. Does that name ring a bell from Easton's class, Zaid? No. Okay. Should, but that's okay. Charge is measured in coulombs. That's a French physicist's last name. Units big C. E is the elementary charge. Measured, well, I'll give you the value for that. The elementary charge is 1.6 times 10 to the negative 19 coulombs. That is the amount of electric charge held by one electron. Interestingly enough, it's also the amount of charge held by a single proton. The amount of charge an object holds has nothing to do with its mass. And then N is, as I said before, the number of charges So if I combine some of these ideas here, just to give you some perspective, 1 amp is equal to 1 coulomb of charge per second. And if you think about what a coulomb, actually I'll make this look like more like a 1. There's a 1. 1 coulomb per second. a single electron has a charge of 1.6 times 10 to the negative 19. So what you actually have here, come on calculator, don't be stupid. What you actually have here is 6.25 times 10 to the 18 electrons make up a single Coulomb. So there's tons of electrons flowing here. Questions, comments, concerns so far? Okay. I'm going to make a note here. This elementary charge, this is the charge, and I said it, I'll just write it. Charge on a electron or protons, using notation that you should have seen in either Science 9 or Science 10 in the chemistry section. E minus is electron, P plus is proton. We've seen this notation before for these particles. Please say yes. Don't just say yes if it's not true, but I want it to be true. Who would you have for science, Tristan? For both, 9 and 10? And you've not seen this. You weren't just away a whole bunch? No. Okay. Are we cool with that being, can you accept that notation? Okay. Okay, so current will not flow through a conductor. You need to have a conductor. Things flow through conductors. They don't flow through what? Does anyone know the opposite of a conductor? You should. Yes, thank you. An insulator. And this goes back to what Luis was talking before when we were talking about thermal energy. When you typically think of conductors, you think about things that will allow electricity to flow. We were talking about heat flowing. Conductors and insulators do the exact same thing to both heat and electricity. They restrict the flow. So current will not flow through a conductor. If I have a piece of copper wire and I shove it into an electrical socket, current will not flow. Why? Well, what you need is something called a potential difference. This is what we're going to talk about later. Difference. Did I spell difference right? Difference is a weird looking word. If you really obsess about the look of the word, it's terrible. D-I-F-F-E-R-E-N-C-E, potential difference. A potential difference is what we call a voltage. That'll make more sense in a little bit. And it's this potential difference. You can think about potential that we had before. If I had a pendulum just hanging there, is it going to swing on its own? No. What do you have to do to it? You have to raise it. What are you doing? Oh, I erased my drawing. What are you doing when you raise a pendulum? You are creating a difference in potential energy. The potential energy of the pendulum at the bottom is 0. Potential energy, mgh. By creating a potential difference, when you let go, this thing will swing. A voltage source is the exact same thing in a slightly different way for electric circuits. It creates a difference that gives these electrons energy to flow. So this is, it supplies energy. And 2, the other thing you need is a place for these things to flow. So we need a complete, or the language we use for complete is a closed circuit. You can give as much energy as you want, but unless these things have a place to go and a way to get there, nothing's going to flow.
That happens in saving because the saving has two things that affect the people. So if you miss one, the circuit is not complete, and the things don't work.
It's true. Absolutely. Do you have experience with tasers?
No, but my mom knows how to use it.
Why does your mother know how to use a taser?
She's a prosecutor. She knows self-defense.
Nice. A prosecutor in Brazil. Yeah, you would think that a lawyer in Brazil, a criminal lawyer in Brazil would know how to use a taser. Yeah, that would be that's a good country to know self-defense. Yeah, Luis is right. If you get hit with one prong of a taser, it's not going to do anything for you. That's why there's so many prongs. because you need that circuit to be closed. And that's the other reason why it hurts so much to get tased, is because you've got these things separated by some distance, and they're building up energy, and energy is lots of it built. As soon as that circuit gets completed, all of that energy has somewhere to go. Fun fact, you can also build, those little handheld tasers that just have two prongs and you shove it into someone? We've seen these before? Okay. You can make one of those yourself. My buddies and I did, using a camera flash. Because a camera flash operates on the same principle that a taser does. Like one of those big, you'd add it to a normal camera, not an iPhone camera. It operates on, you have a large potential difference just sitting there waiting to be used. And all of a sudden the circuit gets completed very quickly. Boom, all of that energy moves very fast, light flash goes bang, and you've got a circuit complete. Now it's dissipated and you start again. If you take out the bulb and put two prongs there, you can build up all that energy, and rather than it going through the bulb and completing a circuit, flashing light on whatever it is you're photographing, you can take out the bulb, rudimentally put in two screws, and then shove it into your buddy, and he becomes the flash bulb. And it hurts a great deal. My buddies and I actually did this at our grad retreat, and we would pass the thing around and we'd shock ourselves. It was fun. Because you can determine how the charge is by how long you allow it to cycle for. Anyway, random and stupid. Hurt a lot, but it was a good time. An application of moving charges. Some examples of voltage sources that you use every day are things like batteries are a voltage source. Electrical outlets are a voltage source. These are likely the only two things that you will use on a regular basis. Interestingly enough, they provide different kinds of energy. Does anyone know the difference between a battery and an electrical outlet, as opposed to the kind of energy they provide? It's current that's different. We'll get there. If you don't remember, that's fine. In a straight line. Yeah, okay, so I'll give you the names. Batteries provide what's called DC, which is direct current, and electrical outlets provide AC, which is alternating current, which is why you need a big plug adapter to charge like your phone. Because your phone, the battery in your phone, provides direct current to all of its electronic components. The wall provides alternating current. And so you need something to convert that alternating current into a direct current to charge your battery so the thing doesn't explode. Fun fact. So, the current in a circuit depends on two variables. We've got I here, depends on two things. It depends on the voltage, the amount of energy supplied, and it depends on the resistance. Resistance is what? Sorry? Resistance is measured in ohms, cool. But what does it mean for things to be resistant? Sorry? No. If I tell you to do something and you resist, what are you doing? You are not doing the thing I'm asking you to do. If I apply more pressure and you still resist, we would say your resistance is pretty high. But eventually, if I apply so much pressure that you cave and do the thing I'm telling you to do anyway, Luis, go jump off that bridge. No, I don't want to. No, go jump off that bridge. No, I don't want to. Now all of us as a class, Luis, 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 and we break down your resistance and you jump off the bridge. We have provided you with enough, potential to wear down your resistance. Resistance is just simply that. How difficult it is. In general, it's how difficult it is to get something to do something. Specifically in electric circuits, resistance is how difficult it is for current to flow. an object. That object could be anything. That object could just be the copper wires. Copper wires have very low resistance. That's why we use them to power or to run electric current through our place. Or there's other objects that have very high resistance. Your lamp, for example, if you have a lamp at home, has a light bulb in it. The reason that that light glows is because the filament in that light bulb, assuming it's one of those old school light bulbs, has a high resistance. So it impedes the flow, causing it to glow. Other light bulbs are a little different, but like the old school ones are a good example for that. So that's resistance. Voltage, we already said. Voltage is a potential difference. Which I'm just going to formalize what I said on the board before. It's the difference in potential energy. In this case, the potential energy isn't gravitational, it's not spring, it's electrical potential energy. And so the potential difference is the difference in potential energy per charge between 2 points. And the units of voltage is probably going to be what? The difference, the units of voltage is probably going to be V, which stands for I know you're all thinking it, no one wants to say it, but volts. Voltage is measured in volts. It's one of those things where it makes too much sense, it's probably wrong. But no, you're correct. Named after an Italian physicist, last name Volta. It's a really cool last name. Units of resistance, as Manuel already said, those units are called ohms, after German physicist, last name Ohm. The symbol is not what you would expect. We don't use O for anything. It's the horseshoe, which is the Greek letter O. No, that's the Greek letter M. The Greek letter O is omega. Looks like a horseshoe, as Manuel already said. So voltage is potential difference. It's the difference in potential energy per charge between 2 points measured in volts. Resistance is how difficult it is for a current to flow through an object in ohms. So if you have a large voltage, it's going to want to create for you a large current unless you have a large resistance, in which case it's going to prevent the flow. So you've got these three concepts working together and against each other to create for us the circuits that we use every day. So the thing I want you to consider is a river. Consider a river. The rate of flowing down the river in my analogy here, well, actually not even in my analogy. In the world, you go down to the Fraser River, you see it flowing. The flow of water we call the current. And when we talk about the current in a river, what we're talking about is the rate of the water flowing, how much water is flowing past you, not the speed that the individual water molecules are moving. So it's not just how quick the water is, it's how much water per time is flowing past us. That's what we define current to be. That's what we define current to be when we're talking about electric circuits as well. The same is true for electric circuits, where the current represents how many electrons pass a point in a certain amount of time. So now putting this all together, we get something called Ohm's law, which you're supposed to learn in grade 9, but lots of teachers don't because there's so few physics teachers that actually teach Science 9. Ohm's law is a relationship between voltage, resistance, and current. So I've got current up here, voltage here, and resistance here. So if I have a large voltage, I want a large current. But my resistance is going to prevent my current from flowing. So these three objects are going to exist in a similar relationship to how we had distance being equal to a velocity times time. The amount of voltage, V, that you need to provide is going to be equal to the amount of current you want times how hard it is to make it flow. And so we get Ohm's law here, that's V equals I times R. The amount of voltage is equal to the current times the resistance. This wasn't how Ohm proposed his law. It's just the easiest way to deal with Ohm's law. The original way Ohm provided his law wasn't in terms of voltage, it was actually in terms of resistance, where the amount of resistance R is going to be equal to the amount of voltage, the potential difference, divided by how much current is flowing through here. So this was the original formulation for Ohm's law. I hope you can see how easy it is to go from this one to this one. We just multiply I on both sides and get V equals I times R. Which means there's also a third one here that'll isolate current. Questions, comments, concerns so far? Maybe it's just Wednesday morning and y'all are tired, but you're very quiet this morning. Okay. So let's keep going. This is just an introduction to current. Next one. Consider then a circuit of a battery connected to a light bulb. Which way does this thing actually flow? Let's draw it. Again, if you did circuits in grade 9, the drawing I'm about to make should make sense. But if you didn't, this is going to be brand new to you. Here's how we draw a battery when we're drawing a circuit. In a battery, there are two ends. You know what? I can just pull out a battery. Here's a battery. Technically, we call this thing a cell, electric cell. The battery has, I don't know if you can see it there. See that right there? What is that? What's that guy right there? Positive end. The positive end is a little stubby end. And a negative end. So when we draw our batteries in our electric circuits, we've got the fat end on the bottom and we've got the stubby little end up top. So that's how we draw a battery. You'd think that we would draw it in order, same as a battery, but you'd be wrong. The fat end is what we call this negative end. Sorry, I lied. The fat end is what we call the positive end, which is not how a battery is designed. It's exactly the opposite of how a battery is designed. And the stubby little end up top, we call the negative end. Again, exactly the opposite of how the battery is designed. And so what we're going to do is we're going to connect this thing to a light bulb. Now, a light bulb is going to be drawn the way, it's going to make sense with the way light bulbs used to be. They used to have a little curly filament inside. So the way we draw light bulbs in a circuit is have something looks like this, with our little curly filament inside a bulb. Unfortunately, most bulbs now don't look like that, and my daughter will likely never see a bulb that looks like this in her life, which is weird to think about. But that's how we demonstrate a light bulb. So we've got my battery is now connected via some wires to our light bulb. Which way does the current flow? There are two ways, right? Either out the top and around, or out the bottom. What's actually doing the flowing? The electrons are actually doing the flowing, right? We've already established this. You're cool with that? So what's probably going to happen is if you have on the battery, if you've got a large source of negative, that is probably where things are going to leave, because as you said before, like charges repel. You said that right at the beginning. So the electrons are going to repel each other, so as soon as they've got a place to go, they're going to start marching down this way. My electrons are going to flow through the lamp towards the positive. That is what would make sense. But circuits have been around for a really long time, and circuits have actually been around longer than people knew about electrons and protons. So if you were building a system that was involving the flow of electricity, and you don't know what that electricity is, would you assume that the electricity is actually negative? Or would you assume that the thing that you're working with is just, we're going to give that a positive quantity and we're going to go with it? Current here is 5. Why would I default to calling it negative 5? That wouldn't make sense. So what happened was, when originally these guys, physicists from long gone, and I call them guys because they were largely men, not large men, but the vast majority of them were men, they didn't know about the electron until a guy named J.J. Thomson comes around, discovers the electron. So what they were doing, they said, oh, well, this is my current's positive. So what's actually flowing here is I've got a positive source of electricity, and my current is flowing from the positive side, and positive things are going to flow to the negative, and so this is what we're going to call our current here, I. So then when we discover the electron, we have two choices. Either we can fix everything that's gone on before, or like a good physicist, you're super lazy and you're like, well, I don't want to change everything we've already done. So we're just going to understand that we are exactly backwards, and we're just going to call it good. So that when I'm talking about current, if you're understanding the flow of electrons, you just are going to understand that you and I mean the opposite direction. Because it doesn't actually matter, the math dictates, it's interesting, it doesn't actually matter which way the current is going. The current just needs to be able to complete the loop. It doesn't matter if the electrons go this way or if the current goes this way. Our current goes the red way. The fact that we want the bulb to light up, it's going to light up either way. So I don't need to undo everything I've already done. We're just going to leave it the way it is. And as Manuel has already said, coming out of the electric outlet, you have something called alternating current. And alternating current is interesting because it actually causes the electrons not to go around the circuit like a direct current does. The electrons just go back and forth like this. Really fast. 60 times per second. And so the electron's not even completing the circuit. It's just going back and forth, jiggling back and forth really quickly. Still makes the lights turn on. So let's now all put this in here into words, into language. There are two ways to consider this. One is by considering electron flow, the directions that the electrons actually move, and the electrons go from the negative terminal on the battery to the positive terminal. That is electron flow. Or, the way we understood it to begin with, this idea of conventional current, which is the flow of positive charge. Positive charge doesn't flow. But if it did, it would go from the positive terminal to the negative terminal. So if these guys had to do everything over, they probably would have called the electron the positive thing and the proton the negative thing. But rather than redo hundreds of years of chemistry, they're just like, we got it wrong. As long as everyone knows we got it wrong and agrees to gloss over that fact, we'll just leave it the way it is and call it good. So in this class, unless we otherwise state it, and everywhere else you talk about electricity, we will always use conventional current. Cool. I'm going to stop here. 20 minutes left. There is no homework out of this stuff. This introduction here is everything that most of you should have gotten out of Science 9, and only one of you did. So, does this bring back some memories of stuff that you've seen before? Okay. For this stuff here? Often in grade 9, they just slap that down and say, you need this. Yeah, this gives you, I'm hoping this gives you a little bit of context for all of that. For you guys all sitting here, does this make sense as far as your understanding of the electric world goes? Are you comfortable with what I've presented to you here? Kind of, sort of. I mean, it's things that are too small to see, moving faster than we can comprehend, powering things that we take for granted every day. So it's pretty wild stuff. Lots of this was supposed to just, is definitions that just build on each other. So I'm just going to let this percolate. You've got a test tomorrow, so we're going to come back to this on Tuesday. And hopefully we're a little bit more comfortable then. Yes, Luis?
Something like, I think that I have a little bit of this, and then she's to introduce, like when the molecules pair and form two different ones.
Yeah, ions. Yeah, that's electrostatics.
I learned something like that in chemistry, but I don't remember much about it.
There you go. Okay. Angelina, Jasmine, you guys said kind of. Is this one of those things where it'll take some time? Okay. Yeah, a lot of language. And it'll make more sense when we start actually using this stuff to do things. But yeah, this is, like I said, this is where I'm going to stop. So use whatever time's left. Consult with me, consult with your classmates, consult with the answer keys about any of the review you guys are working on. Test is tomorrow. After lunch, I believe, A, B, C, D. If it is a short block, an hour, 5 minutes. You will need more time than that, certainly. So either, unless you're like amazingly good at this stuff, so either come at lunch tomorrow to get this thing started, or depending on whether or not you've cleared things with your D block teacher, you can write through D block as well, because I don't have a class coming in here. But I will ask you tomorrow whether your D block, if you talk to your D block teacher. And if you haven't, I won't let you stay. So if you anticipate needing to stay, run that by your D block teacher today, which is the class you have next, please. And if they're cool with it, then you know you've got some more time. Otherwise, you know to come at lunch. So there you go. That's what we're doing today. Nope, I don't want to start streaming. Cancel.